Hi students! In the last lesson, we took a look at arithmetic sequences where the same quantity is added from one term to the next. Today we're going to look at geometric sequences where each term is multiplied by the same quantity to get to the next term. Let's take a look at the definition and then we'll look at some examples. A geometric sequence is a sequence in the form AR squared, AR cubed, AR to the fourth, etc. The number A is the first term, and R is the common ratio of the sequence. R is the quantity that we multiply each term by to get the next term. In this case, the nth term is given by the formula A sub n equals A times R to the n minus first power. The reason R is raised to the n minus first power is to get to the nth term, we have to multiply by R n minus 1 times. So here, AR to the fourth is actually the fifth term. 1, 2, 3, 4, 5. The exponent is generally 1 less than the number of the term. Let's take a look at an example so we can see how these function. If A is equal to 2 and R is equal to 3, for example, we have the following sequence. We start with 2, and then to get to the next term, we multiply by 3. 2 times 3 is 6. And then we multiply by 3. 6 times 3 is 18. And then we multiply by 3 again, giving us 54. And then we multiply by 3 again, giving us 162, etc. Notice that the terms of a geometric sequence are generally growing much more quickly than the terms of an arithmetic sequence. The reason this is the case is because they are modeled off of exponential functions. These are growing in general very, very quickly. Let's take a look at 2 more examples of geometric sequences just so that we can get used to them, and then we'll move on to looking at their partial sums. Let's look at the next example. Let's consider the geometric sequence given by 2, -10, 50, -250, 1,250, etc. In this case, note that the first term is 2, so A equals 2, just like in the last example. But here, let's figure out the common ratio. What do we multiply 2 by to get -10? Well, 2 times -5 gives us -10. Let's see if that ratio is the same for the rest. -10 times -5 gives us +50. And when we multiply by -5 again, that gives us -250. And when we multiply by -5 again, that gives us +1,250. So in this case, R is equal to -5, and we can see that each time we want to go to the next term, we multiply by -5. Notice in this case, because the common ratio is negative, we end up with an alternating sequence with terms that are positive, negative, etc. Whenever we have a geometric sequence where our terms are alternating between positive and negative, that means that we have a negative common ratio. Let's take a look at one more quick example before we move on. Let's consider the geometric sequence 1, 1/2, 1/4, 1/8, 1/16, etc. In this case, the first term, A, is 1, and the common ratio is 1/2. When we multiply one term by 1/2, we get the next term. So in this case, we have a common ratio that's less than 1, specifically 1/2. And if we look at how this affects the individual terms, we can see that instead of increasing very quickly, they're actually decreasing very quickly. They're decreasing exponentially. So we can have different things that happen with a geometric sequence depending on what the common ratio is. If the common ratio is larger than 1, we generally have numbers that are getting very large very quickly. If it's between 0 and 1, we've got numbers that are getting smaller very quickly. And when the common ratio is negative, we end up with terms that are changing signs between positive and negative alternating. Please take a look at some of the example problems below to get more practice working with geometric sequences, and then you can look at partial sums of geometric sequences in the next video.